All right, let's start. Good morning. Good morning. Welcome back. I hope you had a nice break. I certainly did. So we're slightly behind schedule, but not a major deal. So this week we're going to start talking about orthogonality. Essentially, next week we're going to talk about orthogonality as well. Within the world of perpendicularity and stuff, there's a very important algorithm, Gram-Schmidt, that we're going to discuss next week. And then the week after, all of these are going to come together with the eigenstuff, and we're going to have our first major theorem, or maybe the second major theorem, spectral theorem. It's going to be all about eigenvalues, symmetric matrices, orthogonality, and so on. Now, the new problem set is up on Canvas. It's due this Friday. It's about mostly eigenstuff, but there's also some relativity stuff. I'm using there, I think, some terminology. There I sort of wrote a short summary of all of these things. Today and probably tomorrow too, we're going to discuss the remaining concepts that we haven't discussed so far. So far, we were only just focusing on calculating the things and what is the standard operating procedure when it comes to these eigenstuff. OK, are there any questions before I start? So I want to finish discussing this example that we had started last time. I'm going to remind you. It's a 3 by 3. So it's like this. Minus 1, 1, minus 1. And then 6, 6, 8. Okay. Now, in general, you see, if you have a matrix like this that has no symmetry whatsoever, it's not diagonal, it's not lower or upper triangular, whatever, then the eigenstuff becomes rather hard. And on top of that, let's remind ourselves, even though in general row reduction and stuff is still useful, even for eigenstuff, it's not as useful. And so the calculation of eigenvectors and so on, in general, are rather more tedious, especially if you start with a matrix that has no structure like this. Okay. And what are we trying to do? We're trying to remember, we're trying to figure out all eigenvalues, all eigenvectors. And I'm going to define some of the other ideas over there that we're going to need also as we go. So let's just remind ourselves what this eigenequation was. If you have an n by n matrix A, you want to solve AX equals lambda x. So let's write it. That was the eigenequation. Right, so maybe we can write it explicitly. 4, 2, 2, minus 1, 1, minus 1, 6, 6, 8. This times x1, x2, x3 equals lambda times the same vector. And so lambda x1, lambda x2, lambda x3. In short, you can just write it like this. AX equals lambda x. This is the eigenequation. Okay? For a variety of reasons, this is important. We need solutions to this. In principle, you want the x vector to be a three-dimensional vector in R3, or one vector in R3, let's say, that is non-zero. And lambda is some real number. So x non-zero vector in R3 and lambda scalar. Again, real. In principle, this is what you want, but sometimes you don't get to solve the eigenequation using only real stuff. If it comes to that, you're going to go to complexes. Okay, that's okay. Initially, you want R3 and R, but along your calculations, it might happen to be the case that this has no solutions in the reals. Then you're going to transition to complexes. So if needed, use C. Okay. You don't want to use it initially, but whenever you have some rotation hidden inside your transformation, you're going to end up needing to use the complex numbers. Okay, at this point, just by looking at these entries, you cannot quite say, oh, this is a rotation, whatever, or this doesn't have any rotation. This is the eigenequation. Its non-zero solutions X are eigenvectors, okay? And lambdas that solve, again, are eigenvalues. So eigenvalues are scalars, eigenvectors are vectors, okay? And we always look for vectors that are non-zero. I should add here one more word. I'll add the word eigenspace. Somewhere here. Okay. So what was the standard operating procedure? You first set up the characteristic equation. Okay. Characteristic equation. Why? Because as given, because both xi's and lambda are unknown, you're multiplying here two unknowns. And so if you just leave both lambda and x as variable, this is not a linear equation, which means that we don't know actually how to solve it. Instead, what we're going to do is we're going to first focus on lambda, solve for lambda, then solve for x. So characteristic equation for this A is, well, determinant of lambda I minus A is 0. Okay. We've expanded this last time. I'm not going to go through it again. You get this polynomial. So when I say this, so lambda should be variable here. So the variable of my polynomial is going to be lambda also. And so you get this. Lambda cubed minus 13 lambda squared plus 40 lambda minus 36 equals 0. When we expanded this out, we got this. Okay. Why are we looking into this? Let's remind ourselves. Because zeros, or rather the solutions of the characteristic equation, is the same thing as eigenvalues of A. That's the whole point of looking at this. So solutions of the characteristic equation is the same thing as eigenvalues of A. Okay. It's also fairly common to call this, the polynomial on the left-hand side, the characteristic polynomial of A. Okay, it's a polynomial in lambda. So this determinant of lambda I minus A is defined as a characteristic polynomial of A. This is a new terminology now. Char poly. This has multiple different notations. I like using this char sub A of lambda is determinant of lambda I minus A, which instead you can just write this if you want, of course. So this is lambda cubed minus 13 lambda squared plus 40 lambda minus 36. So if you look at the zeros of this specific polynomial associated to A, okay, well, that's the same thing as looking at the solutions of the characteristic equation. In a second, once we're done with this exercise, with this example, I'm going to say more. But for a variety of reasons, it turns out to be rather convenient to think about this as a polynomial function in and of itself. Okay? Because somehow all of these coefficients of the characteristic polynomial tell you certain information about A. So for instance, if you were to look at, let's do some numerology. If you were to look at this, okay, the number next to lambda squared, well, it is minus the trace. Remember, the trace of a square matrix was the sum of the diagonal entries. That's an important thing, okay? What is the trace here? 13. So here you get minus the trace. Okay, this is not coincidental. Okay. It is harder to see what these numbers are. But maybe we can remind ourselves, determinant calculations also. Let's try to remind ourselves what is a determinant or how to compute this. Well, there are multiple methods, of course. I'll use the triangular method. I'll do it here. Since we've taken a break, I thought it would be a good idea to do a small review like this. I want to look at the determinant of this matrix A. Okay, how do we do it? I'll use this triangle method. So I write two of them. Okay, and I'm going to have a plus contributions from triangles in this direction, and then minus contributions from this direction. So this gives me, I'm multiplying everything, right? Well, let's be explicit. 4 times 1 times 8, right? And then I look at this, minus 1 times 6 times 2, and then I look at this, plus 2 times 6 times minus 1. And then I have the negative terms coming from this, minus 6 times 1 times 2, minus this, minus this. Okay. What does this give me? 32 minus 12 minus 12 minus 12 minus 16. No, that's a plus, I think. That's a plus 16. And then plus 24. Okay. These two cancels out with this, right? These two give me 4 plus 32, 36. Okay? Does this match with your calculations? In any event, somehow, you see, the constant term of the characteristic polynomial is the same thing as minus the determinant in this case. Okay. So on the one hand, to compute eigenvalues, it's good to look at the characteristic equation. On the other hand, if you were to just look at the one side of the characteristic equation, that is, again, an important object. It's a polynomial once you open everything up. And each of the coefficients is going to tell you something about A. There is also an interpretation of this number. It's not as easy as the interpretations here. Trace and determinant we've seen before. We'll talk about how we can interpret this number in terms of A also, but later. Any comments or questions so far? Yeah.
If we're not looking at a third degree polynomial,
Yes.
how does that change what coefficients mean what thing?
Yeah, very good. If you were to look at an n by n matrix, characteristic polynomial is going to be a degree n polynomial. It's going to start with lambda to the n. The next one is going to be always minus trace. I'll write it. We're done with this. If A is n by n, the characteristic polynomial is going to start with lambda to the n. Okay. Next, you're going to have lambda to the n minus 1 times some number. That number is again going to be trace, sum of the diagonal entries. Then you're going to have some other terms. And then finally, you're going to have minus 1 to the n times determinant. Yeah. Now, this works if you start with the definition that the characteristic polynomial is determinant of lambda I minus a. If you start with determinant of a minus lambda I, then this top component could have a minus 1. I don't like seeing minus lambda to the n. I like seeing plus lambda to the n. That's why I write it like that. But in some other literature, you might see it the other way around. So sometimes they take it minus this expression, if you want, or minus 1 to the n times this expression. So pluses and minuses end up being somewhat of a contentious issue depending on the literature or the area that you're looking into. This is what I like. I like my polynomials to have plus 1 in the top degree. That's why I use this. Did this answer your question as well? There was another one. Yeah. Any other questions? Okay. So if you see something like this, right? So this is a polynomial of degree 3 with integer coefficients. Then you see a polynomial like this, what you want to do is you want to look at integer factors of the constant term. Okay? And you just fish. There is no sort of easier way to factorize polynomials like this, but ultimately that's what you need. You need to factorize this polynomial somehow. What we did last time was we sort of started with smaller factors, 1 minus 1. They didn't work, but then we looked at lambda equals 2. Try factors, integer factors, factors of the constant term. In this case, minus 36. And we, by experimentation, we figured out one value that works. Okay. In this case, what we found was lambda 1 equals 2 is a 0. Right? So 8 minus 52 plus 80 minus 36, we just computed that to be 0. So we found lambda 1 equals 2 is a solution, is an eigenvalue. Same thing. Okay. Now this is where you end up needing to use some polynomial algebra. Okay. And I'm aware that some of you may be not very comfortable with this, but this is sort of part of the game, unfortunately. And you're going to be responsible to be able to factorize polynomials and find roots and stuff like that. And unfortunately, there are no sort of nice formulas like the quadratic formula There's a formula for the third degree polynomials. It's a lot more messy. Most people don't keep it in mind. There's a formula for fourth degree polynomials, but it turns out that due to very deep reasons, there's no formula for roots of polynomials of degree at least 5. So if the degree is high enough, there is no sort of explicit formula. So, that's a thing. In practice, of course, what you do is, in practice, most polynomials like this are not with integer coefficients. So you employ some sort of a calculus algorithm if you want. If you know, there's Newton, whatever. There are ways to approximate roots of polynomials. But clearly, we're not going to use any of that. For us, it's basic sort of factorization and stuff. So I want to say this, okay? Saying that lambda 1 equals 2 is a solution to this equation, or in other words, it's a root of this polynomial, it's a zero of the polynomial, is the same thing as saying that you can write this polynomial as lambda minus 2 times some other polynomial. Okay, this is the polynomial algebra business. Thus, can write char sub a of lambda equals lambda minus 2 times some other polynomial, p of lambda, for some other polynomial. Okay. Now, because in this case char is a degree 3 polynomial, how can this happen? This can happen only if p is a degree 2 polynomial. You can start with an arbitrary polynomial, expand it out, and match the coefficients if you want. That's one method. I would suggest getting more comfortable with essentially taking this expression and dividing it by this expression, just like you're dividing sort of integers, whatever. Okay. It works pretty much the same way. Maybe I should ask you, how many of you have seen something like this before? You take a polynomial, divide it by some other polynomial. Okay. Most of you. Yeah, I mean, if you're not comfortable with this idea, maybe we can discuss it after class. This is sort of important to be able to do. So I'll do it here. I'll erase this. And so I'm going to take this. I'm going to literally think of it as an integer and divide it by this integer, okay, to find this p. Like I said, because in this case, this guy is degree 3, and this is degree 1, this is going to be degree 2, and I trust myself that once I have a degree 2 polynomial, everything is going to be fine. Maybe I can use quadratic formula, or I can just look at it, whatever. But first, I need to factor this out, because degree 3 polynomials are hard to look into. So, explicitly write it. Lambda cubed minus 13 lambda squared plus 40 lambda minus 36 divided by lambda minus 2. Okay. Now I'm going to multiply this by some polynomial, and when I multiply it, I want to get rid of this lambda cubed. Okay. Because I have a lambda here, I better have a lambda squared here. Okay. So when I multiply these two, I get lambda cubed minus 2 lambda squared. Now, just like with integer division, just because you're fixing one of the digits doesn't mean that you're not messing up other digits. So that's what this corresponds to. So you got rid of the top degree term here, but you messed up the second degree term. Okay, so now you have minus 11 lambda squared, and the rest remains. Again, I look at this and I say, how can I get rid of this top degree term? Well, I better have here a minus 11 lambda, sorry. When I multiply, I get this. And then plus 22 lambda. Again, subtract. These two go away. Now I have 18 lambda minus 36. But you see, this is 18 times this. Maybe your notation is somewhat different. This was how I was taught to write these things. Maybe you write it like underneath or to the side or whatever. But I just did long division basically. Started with this, divided it by this, and I came up with this. So this is my p, you see. This is p of lambda. Yeah.
What if you have a remainder?
You're not going to have a remainder. If you have a remainder, that means that this choice is wrong. Yes. Very good. Either you figured this out correctly, in which case this is going to have a factor like this. Your remainder is going to be 0. Or if you have a remainder, that means that you have to go back because you made this wrong. Yeah. Very good. Any other comments? Okay. But you see, I look at this and I can immediately see how to factorize this. If you don't see it, you can use a quadratic formula, whatever. Right, so if I have here lambda minus 2 times lambda minus 9, and I multiply, I get this. Okay? And so ultimately, then, the characteristic polynomial is lambda minus 2 raised to the power 2 because I have one over there, another one over here, and a lambda minus 9. Okay. Now, remember, we were before looking into diagonal matrices and stuff, or lower triangular and all that. For those type of matrices, the char poly immediately came out as a product like this. That's also one of the reasons why diagonals or lower triangulars and so on are so nice. Char poly comes out factorized. For general matrices, you're going to have to suffer. Okay. Any comments so far?
Will one of the polynomials always be squared?
No. No.
Just a little clarification on that.
Yeah.
So I remember learning about this a couple weeks ago. So if it's a diagonal
Yes.
or lower triangular, then the characteristic equation is those numbers in the diagonal with the.
Yeah. Let's write it here. I still need to define eigenspace, but we'll do it in a second. Here's what I said. If you have a diagonal matrix like this, then the char poly is going to be like this. Lambda minus lambda 1 times lambda minus lambda 2 times lambda minus lambda n. That's what I said. To answer your question, if I were to choose some of these numbers to be the same, I would have exponents like this. But in principle, they could be all distinct. Okay? Same thing with upper triangular. Or lower triangular. Okay? any other comments or questions so far? See, like the algebra is getting more and more complicated. This is the, eventually we're going to start appreciating things like the spectral theorem and the singular value decomposition and stuff. And just to reiterate, if you start with this guy and get smart and do row reduction and then do all this stuff, you're going to get completely bizarre numbers. You're going to compute wrong things. So you don't get to simplify before doing all this. Okay. Okay, I think I'm going to erase this part because I want to keep writing more things. Characteristic equation, characteristic polynomial. But of course, I'm writing these to come up with the eigenvalues, which means that's why I factorized it. But once I factorize this, I have a perfect understanding of all eigenvalues. One eigenvalue is 2. The other one is also 2. And the third one is 9. Okay. Now I can mention this next idea over here, spectrum. Okay. Spectrum is just a fancy word for the set of eigenvalues. Spectrum. Spec of A is set of all eigenvalues. Of A. So in this case, it is 2 and 9. Okay. And typically, you would want to draw the spectrum as a subset of the complex plane. Because in principle, eigenvalues could be complex. So you sort of look at that picture. I would suggest drawing it like this. First draw a circle, and then something like this. That's your complex plane. Okay, so this is the x-axis, and this is the iy axis. This circle is the unit circle. The unit circle is important. What is inside, what is outside? Which eigenvalues are inside, which eigenvalues are outside? In this case, you have one eigenvalue here, that's 2, and somewhere here another eigenvalue, which is 9. Okay. Of course, for our situation, for the types of linear transformations we're looking into, n by n's, or more generally, finite dimension or linear transformations between finite dimensional vector spaces of the same dimension. The set of eigenvalues, in other words, the spectrum, is going to be a finite set. But it turns out that in more general settings, when you're looking into sort of infinite dimensional spaces and so on, signal processing, all these things, the spectrum could be a much different set. So it becomes then very important to understand the geometry of the spectrum. Maybe we'll mention it eventually, but if you're interested in things like this, one of the most fascinating examples of this is what is called the Hofstadter butterfly. Okay, maybe I'm writing the name wrong, but if you search for this, Google is going to figure it out. Okay, comes from like physics. So that you have like a family of linear transformations on an infinite dimensional space. Has to do with what is called the almost Mathieu equation. And so somehow, as you change the parameter, the spectrum sort of changes with your parameterization, with your parameter change. And it sort of like draws a butterfly type of a thing. And it's sort of like a fractal too. It's very bizarre. Like, this is not going to make sense, but like this, and then There's like wings like this, and then inside the wings there are like smaller wings and so on. Very bizarre picture. Some people say this is the image of God or whatever. So, but anyway, spectrum is important. Set of eigenvalues. Okay. Now, what else do we do? Well, for each eigenvalue, for each element of the spectrum, we would like to come up with a linearly independent set of eigenvectors. Oh, even before that, I should define this. Now, it's a conundrum when you have this repetition. Okay? Do you say one eigenvalue or two eigenvalues or three eigenvalues? Okay, that's sort of like a confusing matter. Because of that, people use this word algebraic multiplicity. Okay? In this case, you can say A has two eigenvalues, or two distinct eigenvalues. One of them is 2, the other one is 9. The eigenvalue 2 has algebraic multiplicity 2. Why? Because in the char poly, I see the exponent to be 2. Okay? Here, the exponent is 1, so the algebraic multiplicity of 9 is 1. On the other hand, the algebraic multiplicity of 2 is 2. Exponent in the char poly. So AM of 2 is 2, AM of 9 is 1. Okay, 2 and 1. Yeah.
Is this sort of the same thing as when you would figure out if zeros bounce or go through?
You mean when you plot the characteristic polynomial?
No, just like from like high school, just general.
Say again?
When you found the zeros,
Yes.
there was a way to like figure out if it bounced on the x-axis, like if it bounced it or if it crossed it, based on like.
Yeah, you're looking at the you're looking at the graph of the characteristic polynomial. Yeah, you could do that. You can do that. Yes. It's not bounce or traverse, but it's more complicated. But in a sense, you can think of it that way too. Yeah. Yeah, algebraic multiplicity being odd would correspond to crossing. Algebraic multiplicity being even would correspond to bounce. Yeah, you can think of it that way. Yeah, so we're not going to really try to visualize this function, its graph and stuff. You can, if you know calculus, you can try to approximate its zeros, whatever. But we're not going to do that. But certainly you can try doing things like this. Any other comments or questions? Okay. You see, we're still in the same example. Define the spectrum, algebraic multiplicity. Now I want to find eigenvectors. And I think at this point, I'm going to have to start deleting things. I'll start. I want to keep this. OK. Yeah, we have a better expression for the characteristic equation anyway. OK. So I should say one thing. Now I'm going to condition on these two different eigenvalues to get eigenvectors associated to them. If I plug in lambda equals 9, that's going to give me eigenvectors for 9. And likewise, if I plug in lambda equals 2, that's going to give me eigenvectors for lambda equals 2, for the eigenvalue 2. Now it's important to note these algebraic multiplicities because these are upper bounds on the number of linearly independent eigenvectors you're going to be able to find. Okay? So for instance, for 9, I know, just by looking at the algebraic multiplicity, that there is exactly one linearly independent eigenvector. So the associated null space has dimension 1, okay? So maybe we can start with that. Vectors for, so this was lambda 1. Let's call 9 lambda 3. How do I find eigenvectors? I go back to the eigenequation, okay? I plug in lambda equals 9 and solve. Now, at this point, you can use row reduction. And so, what do I want? I want 0, 0, 0 equals 9 times identity minus a multiplied by x1, x2, x3. Okay, let's open this up slowly. Plug in a. Consolidate. That's a 5. That's a 1. Minus 6. Minus 2. 8. Minus 6. Minus 2. 1. 1. Okay. Let me just double check. Seems to be good. Now we need to do row reduction to find solutions to this, because I don't quite see. Oh, well, I do see, because, for instance, the row sums are always the same. They're all 0. Okay, that's 0. That's 0. That's 0, which means one solution is 1, 1, 1. Vector with ones. Maybe I should write it like this. More generally then, because the row sums are always the same, they're all 0, I can just say that the general solution is x1 equals x2 equals x3 and x3 free. Okay? And so I can just choose v3, the associated eigenvector for 9, to be 1, 1, 1. Vector with ones. Assuming that your eigenvalues are correct, once you try to solve for eigenvectors, or sorry, assuming that your equations for eigenvalues are correct, your calculations, once you plug them in, there should be at least one non-zero solution, okay? If the only solution you're getting is 0 vector, that means that you made a mistake somewhere. Okay? And you can see how mistakes could sort of like trickle down at like multiple steps. But at the very least, if you're conscious about what you're doing, you should always be able, you should always be able to see that things are not quite working out, and then go back and, redo calculations and so on. Okay. Any comments or questions so far? Yeah.
So you said the algebraic multiplicity is an upper bound.
Yes.
So
Yes.
for this one, we would just stop here.
Exactly. Yeah. That's a basis. Very good. And indeed, because the algebraic multiplicity of 9 is 1, and since I know that there's at least one solution to this, like I knew that there was going to be one vector and so on. And the nullity of this matrix was going to be 1, even before computing. Any other comments or questions? We need to do the same thing for the other one. Probably we're not going to be done with this because I still want to say a couple of things. Sometimes people would use different indices for the same eigenvalue. Sometimes they would use the same index, whatever. Depending on the context, that sort of changes. I started using it like this, so I'm just going to keep at it. This time I'm going to look at 2I minus a, like so. And again, remember, because the algebraic multiplicity of 2 is 2, I know that there's going to be at most 2 linearly independent solutions to this. Okay? Even before computing anything. So now compute. Like so. Okay. Minus 2, 1, minus 6. Minus 2, 1, minus 6. Okay, so you see this is really nice. Minus 2, 1, minus 6. You should get something like this. Okay, this is the right thing. There should be redundancies. Okay. But then I can get rid of the second and third rows. And I can just say, what is the general solution of this? It is minus 2x1 plus x2 minus 6x3 is 0. And x2 and x3 are free, let's say. Or maybe x1 and x3 are free. Okay. So you see I have 2 linearly independent eigenvectors. If I were to plug in x1 equals 1, I get 1 vector. And for the other one, I get something else. So if x1 is 1, then I have here this. X2 should be whatever. We'll figure that out. That's 0. So that should be a 2. And then if I plug in x1 is 0 and then x3 is 1, or that should be a 1. If x3 is 1, then this is a 6. Yes, these are eigenvectors. Okay, these are 2 linearly independent eigenvectors. This is the maximum possible. So we're done with everything that we discussed so far. Eigenspace, I'll leave you with this, is the subspace spanned by eigenvalues, eigenvectors. So the eigenspace associated to 9 is the span of this, and the eigenspace associated to 2 is the span of these two. Okay. We have a couple more phrases there that we need to discuss, but that we're going to do tomorrow. Thank you. I'll see you then. All right, let's start. Good morning. I want to finish the discussion of this example that we started. There's still a couple of phrases I want to give explicitly. I want to define explicitly. And then we'll be on our way discussing orthogonality and more geometric notions. And then we're going to spend the rest of this weekend, next week also, with orthogonality. Next week we're going to focus more on this Gram-Schmidt algorithm. And the week after, we're going to look at spectral theorem. So spectral theorem, already at this stage, should mean something to you because I've mentioned it a couple of times, but more importantly than that, the set of eigenvalues we defined as a spectrum. So spectral theorem has to do with the spectrum, okay? It has to do with eigenvalues. Okay, so this was the example that we were looking into. I have this 3 by 3. I'm just going to recap all the calculations we've done so far. 4, 2, 2, and then minus 1, 1, minus 1, and then 6, 6, 8. We want to solve the eigenequation initially. So what did we do? We set up the characteristic equation, or maybe now we can say characteristic polynomial. Remember, the characteristic polynomial was the left-hand side of the characteristic equation. Characteristic equation is nothing but, writing the characteristic polynomial and setting it equal to 0. So this was the characteristic polynomial. I'm thinking of it as a polynomial with lambda as the variable. And so this is, by definition, determinant of lambda I minus a. Okay. And we did some calculations last time, and we figured out that this ultimately looks like this. Lambda minus 2 squared times lambda minus 9. Okay. And so we said, based on this, I have 2 distinct eigenvalues, or 3 eigenvalues with multiplicity. So I can just say spectrum of A is the set that consists of 2 and 9, these 2 numbers. That's a spectrum. Then we went ahead and plugged in these different values for lambda in the eigenequation to solve for eigenvectors. Okay, we found for these, we found something, and then it was like this. I think this was minus 2x1 plus x2 minus 6x3 equals 0. We did some calculations, and that was the equation that we came up with. And so if I were to plug in x1 is 1, x3 is 0, that would give me that x2 is 2. And so I'm going to have v1 to be 1, 2, 0. On the other hand, if I were to choose x1 to be 0 and x3 to be 1, then x2 is 6. So that I have here 0, 6, 1. Okay. We also just computed an eigenvector for this, for the other eigenvalue. V3 was the vector of 1s. Okay. So this is where we were. This is where we ended up at yesterday. Any questions or things I should go over again? Again, like I told you, I fast-forwarded the first part of this course because I wanted to sort of slow down when it comes to eigenvalues and eigenvectors. Now, we're using the same ideas that we've been using for quite a while now, but somehow this eigenstuff really requires that you sort of transition from thinking one way to another in a rather sort of fast way. And so I think it would be good if you have any questions to sort of slow down and discuss them. Okay. Okay. Yeah, so maybe I should ask you then. Now that I did these, how can I verify that my calculations are correct? In other words, I have one eigenvalue which is equal to 2, and I was able to come up with two vectors. Neither of these are 0, so they could be eigenvectors, and they certainly are linearly independent because only the first vector, for instance, allows you to move in the first direction, and likewise only the second vector allows you to move in the third direction. So these are indeed linearly independent, but how do I check that these are indeed correct? How can I verify?
You just plug those vectors into your actual transformation.
Okay, exactly. So if you have something like this, what you can do is to check that these calculations are correct, well, you just take one of these vectors, left multiply them by this transformation, and it should give you back the same vector up to the corresponding scalar. Right? So ultimately, we were always trying to solve the eigenequation. So all this stuff that we were doing so far was so that we could solve the eigenequation. I'll just do one of these. Check. Or maybe we should do all three of them, just to remind ourselves how to multiply things and so on. Right, so this is A. I'm taking V1, for instance. It's going to give me a 3 by 1. Why? Because I'm multiplying a 3 by 3 against a 3 by 1. Right? So ultimately, this is a valid matrix multiplication, and it's going to give me a vector again. Okay. Right, so how do you do this? Well, the left one you split into rows. To get the first entry here, you take this guy and dot product it with this. Right, that was another word for this. So I take this guy and I'm sort of matching the corresponding entries. 4 times 1 is 4, minus 2 is 2. Okay. For the second entry of the output, now I'm going to dot this with this. 2 times 1 is 2, plus 2 times, or 1 times 2 is 2, so that's a 4. And of course, this is 0, which means I'm going to get back 0. So you see, this is exactly 2 times 1, 2, 0. So if I were to ask you, oh, verify that this is an eigenvector, whatever, say I give you a transformation, an n by n, or 5 by 5, whatever, I give you a vector, 5-dimensional, and I ask you, verify that this is an eigenvector, all you need to do is to multiply and realize that once you do this matrix vector multiplication, it reduces to scalar vector multiplication. Comments or questions about this? I know we've been doing this for quite a while now, but I thought it would be good to sort of slow down and remind ourselves. Let's finish the verifications here, just to be super clear. Because somehow this eigenstuff really does creep on you, okay? 0, 6, 1. Okay. Let's multiply. This by this is 0. This by this is minus 6. This by this is plus 6. So I get back a 0. This by this is 0. This by this is 6. This by this is 12. This by this is 0. This by this is minus 6. This by this is 8. Okay, so you see, this is again twice the input vector. Okay. And then the third verification goes like this. I think I'll continue here. This, right? So right multiplying a 3 by 3 by the vector of 1s really corresponds to the row sums, right? So I'm just going to take this, add each of the terms. 4 minus 1 plus 6 is 9. 2 plus 1 plus 6 is 9. 2 minus 1 plus 8 is again 9. And again, this is 9 times 1, 1, 1. Okay? Yes?
So the outside numbers of like the answers, like 2 to the like 1, 2, 0, and 2, yeah.
Yeah.
So those are actually the lambda values?
Exactly, yes. Very good. Yeah, so maybe I can write it like this. So this really showed me that A times V1 equals lambda 1 V1. Okay. This shows me A times V2, see V2 is that guy, again lambda 2 times V2. And then this shows me that A times V3 equals lambda 3 times V3. These are all solutions of the eigenequation, as you see. Any other comments or questions? Yeah.
I was going to say, I remember us talking about like a class or two ago how the solutions to the eigenequation, like the eigenvectors, are really kind of just a basis for this like line that solves it. Like this line just gets scaled by this transformation.
Yes.
When we have the same eigenvalues, and so we're finding like these two, I guess, related vectors, is it still just that those lines are getting scaled, or is it actually the plane that they span that's getting?
You can think of it either way, because we're only looking at linear transformations.
Okay.
Yes. If you had nonlinear transformations, then that would be an important thing to look into. But part of the beauty of linear transformations is if it scales along this direction and in this direction as well, you can think of it as scaling the whole plane spanned by those things. Yes. So linear transformations are those functions whose input values or inputs can be split into components. And you can just add component by component to get the output. Yeah. Very good. Any other comments? Okay. Now, in a sense, so you see there are infinitely many solutions to the eigenequation, of course. Even for instance, if you were to fix lambda, say, to be 9, here's one solution. But certainly if you were to scale this V3 by some other number, that would again be a solution. So that's why we're looking at the span. And in a sense, we've done all there is to be done for the purposes of solving the eigenequation. But now I want to interpret this even further. Okay? So let's introduce more terminology. We had last time talked about algebraic multiplicity. What was the algebraic multiplicity? This was an integer that you would associate to each eigenvalue based on the exponent you see in the characteristic polynomial. And so in this case, we said, oh, the eigenvalue 2 has algebraic multiplicity 2. And that's why I wrote 2 of these, for instance. On the other hand, the eigenvalue 9 has algebraic multiplicity 1. So, okay, and maybe I should say lambda minus 9 raised to the power 1. Okay, this is the AM, algebraic multiplicity of 9. On the other hand, once you fix your eigenvalue, the number of linearly independent eigenvectors associated to it is the geometric multiplicity. In this case, they turn out to be the same. So, And in this case, I was able to find only one of them. So the geometric multiplicity of 9 is 1. Furthermore, the span of all eigenvectors associated to 2 is the eigenspace of 2. So maybe say E of 2. Eigenspace of 2 is the span of V1, V2. This is the eigenspace. It's a plane. Eigenspace associated to lambda equals 2. And E of 9, again, is the span of 1, 1, 1. Span of V3. This is the eigenspace associated to lambda equals 9. So here's the formal definition for these. Definitions of GM and definitions, GM and the eigenspace. I'll write it, I think, here. So if I have an n by n, okay, then for lambda and eval eigenvalue of A, am of lambda, or maybe I should say lambda 0, am of lambda 0 is the exponent of lambda minus lambda 0 in the characteristic polynomial of A. Of lambda minus lambda 0 in the char poly of A. Eigenspace associated to lambda 0 is E of lambda 0. Notations for these are not really sort of fixed. Depending on the literature, you have like different notations. Sometimes people use R here because it's also called root space for whatever reason. But let's just leave it like this. E of lambda 0 is the span of all eigenvectors associated to lambda 0. But what are eigenvectors associated to lambda 0? These are nothing but vectors in the null space of a certain matrix. So I can just write it like this. This is the null space of lambda 0 I minus A. Okay. And geometric multiplicity of lambda 0 is nothing but the nullity of this matrix. Nullity of lambda 0 I minus A, which is of course the same thing as saying it's a dimension of E of lambda 0. Things are getting confusing, okay? So you see we're only using things that we've defined so far, but the interpretation is somewhat different. Part of it is that we have this variable lambda. And so as lambda varies, things change. The important thing that I mentioned last time is, insofar as lambda 0 is an eigenvalue indeed, well, GM is going to be at least 1. And it's always going to be upper bounded by AM. Okay, this is very important. I'll write it here. This is a very useful inequality. So if lambda 0 is an eval of A, then one lower bounds, what was it, gm, which itself lower bounds am. Okay. This is very nice because based on the standard operating procedure that we discussed, first you're going to compute am anyway. So that's going to give you a sense as to how many linearly independent eigenvectors you should be expecting given any eigenvalue. Defined eigenspace, geometric multiplicity. Okay. Any questions or comments about this? Yes?
Is there a major difference between the algebraic multiplicity and the geometric multiplicity?
Yes. In this case, in the examples that we've been looking so far, at least in most of them, they were the same. But okay, I'll give the example. I'll mention this. In general, gm is not going to be the same thing as am. It's an upper bound. So look at this. This is the main example. Okay. Consider, for instance, A to be like this. It's an upper triangular. This is, in fact, one of the standard forms in this business, but probably we're not going to mention that. Let's just look at this for now. This is upper triangular. We know that the characteristic polynomial of an upper triangular like this comes out split already. What is the characteristic polynomial? Lambda minus 2? Okay. Lambda minus 2 raised to the power 3. So it has one eigenvalue, which is only 2. Okay, the spectrum has only one thing. There's only one energy level, if you want. So am of 2 is 3. 3. So gm of 2 then could be either 1 or 2 or 3 in this case. Well, we need to just look at the equation, right? So gm is the same thing as the dimension of the eigenspace of 2. Eigenspace of 2 is the same thing as the null space of 2 times identity minus a. What is 2 times identity minus a? Well, you just get rid of the diagonal entries, and you're left with this. Okay, you're looking at the null space of this for eigenvectors associated to 2. What are the solutions? Well, x2 has to be 0, x3 has to be 0, x1 is free. So E of 2, the eigenspace associated to the only eigenvalue 2, is nothing but the span of 1, 0, 0. So gm of 2 is 1. These type of matrices are pretty much the only obstruction to gm being less than am. There is a concept called generalized eigenvector that sort of rectifies the situation, but probably it's not a good idea for us to get into that. But there is like more theory behind this. Okay, this is only the starting point. So far, ultimately, let me put it this way. ultimately you want to use eigenstuff, say in the context of linear ordinary differential equations, the stuff that we discussed so far will not be sufficient. You will need to go further, even for linear equations. Okay. If you want to look more into this stuff, you want to look at Jordan normal form. Okay. Or maybe I should say Jordan, because he's French. Normal form. I'll give you one exercise. I can just adjust this example to come up with a matrix with exactly one eigenvalue, whose algebraic multiplicity is 3, whose geometric multiplicity is 2. Okay, I can do that too. So for instance, I can look at this. I guess I'll use red. So exercise. So A equals, so if I delete this one, then what I need works out. Okay, I'm really thinking of this as a block matrix like this. So this is going to have, char is going to be the same, because it's still upper triangular. So AM of 2 is 3. GM of 2 is 2. Okay. More generally, here's another exercise. I can just look at this guy. I'll just call it J. This is what is called the Jordan block. So if I were to look at an n by n that has the same entries lambda 0 on the diagonal and 1s on the first off diagonal and everything else 0, then this is going to have AM of lambda 0 n, GM of lambda 0 1. So deep in theory, these what are called Jordan blocks end up being the most sort of pesky things to deal with. Okay. The best case, of course, is when GM equals AM. That's the best case. It's just that you don't always have it. Any comments or questions about this? Now, I want to go back to the example. I want to finish the discussion of it. In the example, remember, we had, well, one of the eigenvalues was repeating, but AM of 2 was 2 also. And AM of 9 was 1. So GMs were maximum possible. Okay. In particular, A is 3 by 3, so it's a linear transformation in three-dimensional space. I'm going to call A in such a situation diagonalizable, meaning a transformation is diagonalizable if there's a basis consisting of eigenvectors. That's called an eigenbasis if you want. I think I'll erase this. And this is where relativity comes back into play. A is diagonalizable if let me put it this way perhaps. Either one of the equivalent conditions hold. Equivalence Rn has an eigenbasis of A, or there's an eigenbasis of A. So there is a basis of Rn consisting of only eigenvectors of A. Evex of A. Alternatively, you can say it this way. Up to a passive transformation, A is diagonal. Up to a change of basis matrix, up to a passive transformation, A is PDP inverse, transformation P, A is PDP inverse, D diagonal. So relative to a certain basis, which is this basis made up of eigenvectors, well, A is in fact diagonal. It's kind of hard to parse. In this example, it looks like this. So, okay, I'll keep these verifications perhaps. I'll delete this. In fact, I'll delete this as well. So example, the previous example continued. So A was 422, minus 1, 1, minus 1, and then 668, I think. Yeah, 668. Now put D to be the diagonal matrix whose entries are the eigenvalues, 2, 2, 9. Okay. But also define P to be the matrix whose columns are the eigenvectors that are linearly independent. It's perhaps slightly harder to see, but for instance, we have already discussed how these two are linearly independent. Whenever you have two vectors that are associated to two distinct eigenvalues, they're going to be automatically linearly independent also. So you can just take all three of them, put them in a matrix. Like so. So now this is 1, 2, 0. Second vector is 0, 6, 1, and then the third one is 1, 1, 1. I'm saying that A equals PDP then, PDP inverse. Okay, this inverse exists because these vectors are linearly independent. And then if you want to, instead of doing this, you can just multiply AP. If you multiply this and this, you're going to get P times D. So A is diagonalizable. Why do people use this P notation? P, I think, stands there for a passive transformation. P literally is the change of basis matrix from the standard basis to the eigenbasis, basis with vectors v1, v2, v3. This stuff is not easy at this point, okay? So everything is sort of coming together and interacting with each other. I realize that. So you want to always like take your time and slowly go through things. So just to give you an idea, let's verify this. AP equals PD. So you see this is a factorization. And this specific factorization is called the diagonalization. If you can write A in the form PDP inverse for D diagonal, You call that a diagonalization of A.
Question.
Yes.
How did you get P? One more time.
I just took the eigenvectors that I had computed, put them in a matrix.
Okay.
Yes. What I want to do is I want to in fact verify this AP equals PD. You can think of it that way. You can think of writing the transformation A relative to the basis given by V1, V2, V3. In other words, A is the same transformation as D up to this passive transformation P. Yeah. What I want to do is I want to check AP equals PD here. This is like magical in a sense. Takes a while to, accept intellectually that this stuff works. Okay. Check. Let's say star. I want to check this guy. So A is 422 minus 1, 1, minus 1, 6, 6, 8 times this 3 by 3. This was 1, 1, 1, and then 2, 1, 0. No, 1, 2, 0, I think. Yeah, 1, 2, 0, 0, 6, 1. Okay, that's a matrix-matrix multiplication. It's going to give me a 3 by 3. We had already done this, in fact, this verification that these columns are eigenvectors was pretty much calculation of this matrix-matrix product, but let's go through it again. It's going to give me a 3 by 3 ultimately. Okay. Right, so for this, I need to look at this. Right, 4 minus 2 is 2. And what do I do? This by this by this is 0. This by this by this is, just add all of them, 9. This by this by this is 4. This by this by this, 12. Just add all of them. That's a 0. That's a 2. Just add all, get this. Okay? But you see, this is the same matrix that we started with, except that all of the columns are scaled by a number. How do I do column operations? Well, row operations was left multiplication. Column operations are right multiplication. So for instance, if I want to get this, I can just scale it like so. And then I want to divide this by 2. Like this. That's a 2. Then I want to divide this by 9. That's a 9. Which is P times D. Okay. So you see, even though in principle this matrix that we started with was 3 by 3 and it was like a pain to come up with the eigenvalues, eigenvectors, whatever, ultimately all this stuff really tells us that if things work properly, you get to pretend that A is in fact a diagonal matrix up to this pesky passive transformation. But let me just pause it here. These passive transformations in this situation, they're not that big of a deal. It just says, just if you just look at your space in a different fashion, you're just going to see, a very nice matrix to use. For instance, one usage of this diagonalization is taking powers. We had seen all the way back in week 1, I think, we could have a dynamical system, and we would sort of store the time evolution of that dynamical system in a matrix, and then progressing time corresponds to taking powers of the same matrix. So in principle, if I want to figure out the asymptotics of my system, I'm going to need to compute a to the n for n large. Matrix-matrix multiplication, or taking powers, whatever, in general, they are very expensive, but taking powers of diagonals, they are very nice. They are very easy. So for instance, a to the 2, right, is, I'm going to replace it by PDP inverse. These two cancel out, and you get P d squared P inverse. And more generally, the same thing works. A to the n is, or maybe I should say capital N, P d to the capital N P inverse. And in this case, it's going to be, for instance, what was d? D was this. It says 2 to the n, 2 to the n, 9 to the n. Okay. So it's going to be a lot cheaper to compute this matrix, assuming that you have the passive transformation P, to compute a to the n, as opposed to computing a to the n by hand by just taking powers one by one. Okay. So up to this passive transformation, or if you're more familiar with calculus, imagine this P to be something like the analog of the polar coordinates or whatever. So for some integrals, you change the coordinate system, you do a U substitution, whatever, and now integration is a lot easier to compute. It's a similar idea. And this is also one of the reasons why eigenstuff is one of the main exports of this class, like I mentioned a while ago. There is no debate as to whether or not linear algebra is useful, and this is essentially one of the reasons, the main reason. Comments? Questions? Now, the final type of complication that we would need to discuss is this business with complex eigenvalues. Let's just give one example. Because somehow, depending on the discipline that you're sort of trying to contribute to or trying to read, the answer kind of changes a little bit. So for instance, I don't quite like complex numbers in my day-to-day thing. It's like I don't quite use complex numbers. I'm kind of scared of them. I don't quite understand them. So if I have, for instance, this matrix, okay? This is a matrix. This is the matrix that corresponds to rotation by 90 degrees. Whenever you have a rotation, you should expect complex eigenvalues, okay? That's the general idea. That's a rotation by 90 degrees. I'm expecting complex eigenvalues. Look at the char poly. Right, this is determinant of lambda I minus A. What is this? This is the determinant of lambda here, 1 minus 1 here. So lambda squared minus minus 1, which is plus 1. Like this. Lambda squared plus 1. This has no real zeros, right? That's the whole point of the complex numbers. Either you stop here and you say this has no real eigenvalues, but you know, in certain fields, in physics, whatever, in signal processing, you end up needing to use complex numbers. And so if you're allowed to use complex numbers, then you can split this into lambda minus I lambda plus I. Okay? That's literally the definition of this imaginary eigenvalue, or imaginary number. And so the spectrum of A would be plus and minus identity. Plus and minus imaginary number. So if I were to plot this in the complex plane, the spectrum would look like this. Draw the unit circle. This is the x, this is the iy axis. I have two eigenvalues. One of them is here. The other one is here. That's the spectrum. Okay? The point is that even though this is kind of bizarre, this complex eigenvalue, you can just go through the linear algebra pretty much the same way that we've been used to, that we're used to. You just plug in and you just find complex eigenvectors. So, so I look at I times I minus A. Right? So this is I0, 0, I. You have seen complex valued matrices before with Pauli matrices and stuff. So you just go through everything the same way. Okay? Algebra is going to work. It's just harder to visualize what is actually happening. So this is plus 1, this is minus 1. You want something in the null space. If I want something like that, I can just turn it into this. But then that gives you not 0. So if I put minus here, that's an eigenvector. Okay. Okay, what is the span of a complex vector? You have to domain expand, I guess. So this is like a complex thing. It's like, don't worry too much about what this would mean. But you can at least formally write these kind of things down. Okay. It's kind of harder to visualize and understand these spans with complexes and stuff like that. But yeah, so algebra works pretty much the same, and I would just suggest don't think too much about the geometry when it comes to complex stuff. All you should know is that when you have a rotation involved in your matrix, you're going to get some eigenvalues that are complex, and vice versa as well. Okay, that's it for today. We're going to continue tomorrow. Thank you. All right, let's start. Good morning. I'm going to take attendance today. So we're pretty much done with determinant, or rather eigenstuff, at least for a while. I should write it here. Take an attendance. So now what we're going to do is we're going to take a break for a while from this stuff. Focus on what is called inner products, or rather orthogonality and things like this. So this is chapter 6 now. Okay. So I want to start with what is called the inner product. We had in fact defined this a while ago for at least Rn. We called it dot product of two vectors. So we're going to have something called an inner product, which then gives you product, the same thing as dot product. Or sometimes you might also see scalar product, but downstream from it, we're going to have something called a norm. Okay. Downstream from it, we're going to have something called the distance. And also, going back to inner products, we're going to have a notion of angle between two vectors. So as you see, once we define this inner product, we have a lot of geometric notions available to us. Okay. Let's see. Thinking if I should give the general definition first. Because we had already defined dot products, maybe I'll write it first, just to remind you. Okay. So here's an example. Say you have these two three-dimensional vectors. So U is 2, -5, and -1. And V is 3, 2, -3. Okay. So these are two vectors in R3. Okay. What was the dot product of these two vectors? So inner product, the same thing as dot product of these two is this. Okay. I'm just going to write a couple different notations that you might see around. So U dot V. Especially in calculus, this is the notation you use. This is like in distinction with cross products. There's a different type of a product. Never mind. You can see this, or you can see this notation. What is this? All you need to do is, well, you take the left one, transpose it, okay? Then you multiply. Right? So because U is 3 by 1, U transpose is 1 by 3. So you're multiplying a 1 by 3 against a 3 by 1. Ultimately, this is going to give you a number. It's going to be a scalar. Inner products are always scalars. So let's compute this. This is 2 -5 -1 times 3, 2 -3. Okay? So you do this matrix multiplication. What does this give you? 2 times 3. And then plus -5 times 2 plus -1 times -3, which is 6 minus 10 plus 3, which is -1. So that's the inner product. As you see, it gives you a number. Okay. There's nothing special about 3 here. You can just take two n-dimensional vectors and likewise take the left one, transpose it, multiply it against the right one. That again would give you inner product in Rn. And you can do this more generally. Even in infinite dimensional infinite dimensional vector spaces, it ends up being very useful to be able to define an inner product because of all of these things, right? So once you have an inner product, you get to talk about these other more geometric sounding notions. So I think it would be a good idea to give the axiomatic definition. Okay, it's not very sophisticated of a definition. Okay. Take a vector space. Doesn't need to be finite dimensional, but of course in our case it's mostly going to be finite dimensional. An inner product on V is a function right, so I'm going to perhaps use this notation. I want to think of this as a function that takes two inputs as vectors. So I might write it like so. goes from v to v, v times v to reals, such that three things hold. First of all, if you were to fix the first entry to be one vector, then with respect to the other one, it's a linear transformation. So v, let's say ci wi, like so. This is the same thing as, well, you get to pull out the linear combination stuff. Okay. You get to flip the orders. Okay. V against W is the same thing as W against V. And you have also, if you dot anything by itself, it's always going to be non-negative. And V against V is 0 is the same thing as saying V is 0. Okay. Don't worry. Say again?
Sorry, what is VS?
Vector space.
Oh, vector space.
Yes. Don't worry too much about these axioms. Suffice it to say, this dot product certainly satisfies it. One of the important examples of this is in the context of matrix spaces. You would like to be able to take inner products of matrices also. So if I were to look at the space of m by n's, then what I can do is I can define their inner product to be this. Okay. I can't quite multiply A and B, but I can certainly multiply B against A transpose. Okay, because if A is m by n, A transpose is n by m. And so this product is going to be a square matrix, but then I can take the trace of that to get a number. Okay, this is one of the most important inner products that are used. I believe this is what is called the Frobenius inner product. I'll write it. Frobenius. Product. Maybe we can do an example. Let's just look at this in the context of 2 by 2s. So for instance, 2, 1, 1, 1 against 1, 0, 1, 0, say. Okay. I want to compute this. How do I do it? Well, I'm going to transpose this, but it's the same thing because this is symmetric. Multiply these two and then take the trace. So trace of 2, 1, 1, 1 times 1, 0, 1, 0. Like this. Now you need to multiply. Remember, you don't get to distribute trace over matrix-matrix products. That's the property of determinants. Okay. Trace is a linear transformation. So when you do this multiplication, what do you get? You get 3, 0, 2, 0. Okay. So what is the trace of this? 3. Sum of the diagonals. Just works the same way. Maybe I should give one more in the context of polynomials. What you can do is you can take two polynomials, multiply them, get another polynomial, integrate. Take arbitrary two polynomials, okay? And then take their inner product to be this. Say you integrate from -1 to 1, P of x times Q of x dx. Okay, this is slightly harder to write down or verify, but it certainly is an inner product. It's one of the most important inner products, in fact. Yeah. There are many others. If you want, you can change the endpoints of the integration to get different things, whatever. So this is a lot of uses. If you want, you can put here sort of like a density if you want. You can multiply P, Q, and you can have a row to have like a mass distribution, whatever. There's a bunch of different variations of this idea. The most important thing for us is, of course, this case, in the case of Rn. Any comments or questions so far? Now, the reason why I wrote this abstract definition is this, okay? Now, because v against v is always non-negative, you can always take the square root of it, this expression, and that gives you the norm. Norm induced by inner product. Norm induced by inner product is, I just write it like this. V in absolute value, typically you would see 2 bars. I find it more convenient to write it like this. V against V, inner product, then take the square root. See, that's a non-negative number also. So let's compute norms of these vectors. So for instance, what is the norm of u? First, you need to compute u against u. Okay. I'll compute u norm squared so that I don't have that square root. So u against u, what is this? 4 plus 25 plus 1. That gives you 30, which means that norm of u is root 30. Okay. So we compute it. Let's compute the norm of v also. 9 plus 4 plus 9, 18 plus 4 is 22. So the norm of v is root 22. Okay? Yeah.
Is norm synonymous with magnitude?
Yes, you can think of it that way too. Same thing as magnitude. You can call the norm magnitude, or you can also call it, you can also think of it as how distant v is to the origin. Or in other words, if you're interpreting a vector as an arrow, what is the length of that arrow? So I should write those. Okay. Any other comments or questions? Let's continue with the Frobenius example. What is the norm of A? Okay, so now we need to compute A against A. So take the square of A and then look at the trace. Right, so all I need to compute is the top left entry and the bottom right entry. So that's for 5 and then 2. Plus 2 is 7. So the norm of A is root 7. Just write it here. It's probably good practice to write this is with respect to Frobenius, because there's other sort of norms and inner products that are very useful in applications. So put a fro here. There are other ones. Okay. One of the reasons why this Frobenius is nice is because it is in fact not very different than this one. So for instance, imagine 2, 1, 1, 1 as a 4-dimensional vector. 2, 1, 1, 1. Okay? Applying this definition, I would look at the squares of entries and add them up. 4 plus 1 plus 1 plus 1. That's 7. So this Frobenius inner product or norm, whatever, for matrices matches with this standard dot product if you store whatever matrix you have as a column matrix. So that's why it's rather useful. Let's perhaps compute the norm of one polynomial, say x. Okay. What is the norm of p? P against p. Okay, so this kind of requires calculus, of course, but if you don't know calculus, don't worry too much about it. So this is p times p integrated, so x squared integrated. Okay, and what is this? X cubed divided by 3, where x goes from -1 to 1. And so this is double, 1 over 3. This is 2 over 3, for instance, which means that the norm of x is 2 over 3 in square root. So you can do these calculations. Like I said, this last one needs that you know how to integrate things like this, fundamental theorem of calculus, all that stuff. So don't worry too much about that final example, but certainly these two examples you should be familiar with, and especially this example. Okay? Comments, questions? Define inner product, define norm. Let's define distance. Well, I'll add it here. Distance between two vectors is going to be the norm of their difference. Okay? D of VW is the same thing as V minus W in norm. Okay. Running out of space, so I might as well just delete some stuff. Say, in this case, I want to figure out what the distance between these two are, or these two is. So you see, it's all downstream. Distance is defined in terms of norm. Norm is defined in terms of inner product. So you always start with inner product in a sense, at least for our situation. And so what is the distance between u and v? Well, by definition, it is u minus v in norm. And so let's look at this. So this minus this is -1, and then -7, and then 2. The norm of this. Add the squares of each entry. 1 plus 49 plus 4. And then take the square root. That's 54 in root. That doesn't factor, right? So that's as far as you can go, probably. Okay, that's the distance between the two. In a second, I'm going to draw a picture, but maybe in 2 dimensions it's easier to see. Let's look at the distance between A and B. So these two guys. What is the Frobenius distance between these two? Frobenius distance between 2, 1, 1, 1 and 1, 0, 1, 1, 1, 0, 1, 0. This is the same thing as the norm of their difference. What is this? This is 1, 0, 1, 1. It's a shear matrix. Okay, so this is root 3. Because why? Because this Frobenius norm whatever is all about taking this matrix, thinking of it as a vector. And so if I'm trying to compute the norm of this, how am I going to do this? I'm going to take the squares of each of the entries, add them up, and then take the square root of the final result. So we can fast forward everything like so. Maybe let's do one example here. Let's compute the distance between x and 1. With respect to this, so distance between x and 1 is the same thing as the norm of x minus 1, which is the same thing as integral from minus 1 to 1, x minus 1 dx in square roots. What is this? This is x squared divided by 2 minus x. That goes from minus 1 to 1 in square roots. This guy is an odd function, so you don't need to write it out if you want. This is going to give you 1. Okay. Good. These are the examples. Oh, the final thing is angle. I'll give one major statement. This is what is called the Cauchy-Schwarz inequality or Cauchy-Bunyakovsky-Schwarz inequality. There's a relation between inner products and norms. After I say this, I'm going to go back to two-dimensional setting just to convince you that all of these match with your geometric intuition. I think I want to keep that. I'll erase this part, I think. Yeah, okay. We defined inner product, norm, distance. Angle is going to come from this theorem that I'm going to state. So I'll write it in red. Cauchy-Bunyakovsky-Schwarz. I might be spelling these names. It just says this. Inner product of two vectors is upper bounded by v norm times w norm. And in fact, in absolute value, you can put. Okay, this is very useful. Now, based on this, what you say is this. So everything here is a number. And this inner product is upper bounded by v norm times w norm, and lower bounded by minus v norm times w norm. Either both of these vectors are 0, in which case there is not much to do. But assuming that the vectors are not 0, the norms are going to be positive numbers, which means you can divide everything and get this. V against w divided by v norm, w norm. This is upper bounded by 1, lower bounded by minus 1. Okay, if that is the case, we know cosine varies between minus 1 and 1. I can define the arc cosine of whatever this number is as the angle between. Angle between v and w is arc cos of this. V against w divided by v norm, w norm. That's the angle. The most important angle is, of course, 0, which is when v and w are proportional. They are in the same span. And the second most important angle is 90 degrees. And that's when you call two vectors orthogonal or perpendicular. I'll write it in a second, or maybe I'll write it here. Here's the thing. Perpendicular or orthogonal if this is 0. Okay. Why is that? Because, well, orthogonal should mean angle is 90 degrees. If the angle is 90 degrees, the only way that can happen is if this is 0. The only way this can happen is if the numerator is 0. That's why. V against W equals 0 is your equation for orthogonality. At first glance, computing angles, arbitrary angles, is not very important. What is most important is that you are able to compute whether or not two vectors are orthogonal or not. So, is the angle 0 or not? So you just look at this dot product, see if it is 0 or not. Sometimes you might see this notation as well, V, and then this. Okay? This would mean these two are perpendicular. You read this as perp. Okay. So let's compute. Are these two orthogonal? Well, we just dot 6 minus 10. 6 minus 10 plus 3. This is definitely a number that is not 0. These are not orthogonal. Okay? Okay. They have a positive angle between them. Again, we had computed the dot products of these, not orthogonal, and likewise, you can do similar things here too. Let's not worry about this. Okay. Now, the vectors that seem like orthogonal should be orthogonal, of course. So for instance, in Rn, if you were to take standard vectors, they should be orthogonal to each other. That is indeed the case. Let's do it really fast. I think at this point I can erase all this. And in fact, I think at this point it's good to focus our attention to the plane case. So all these ideas match with your intuition from planar geometry. Okay? Distances, norms, and all that stuff. So let's focus on the case when your vector space is R2. So for instance, I can take, well, I have this E1, which is 1, 0, and then E2 is 0, 1. Certainly these should be orthogonal. One of them is the horizontal axis, the other one is the vertical axis. That certainly is the case when you dot these. Dot E2, right? So this by this is 0, this by this is 0, 0. So E1 is perpendicular, you see, to E2. Good. E1 plus E2 is perpendicular to E1 minus E2. So this diagonal is perpendicular to this diagonal. You dot it like this. All right, so what is this? This is 1, 1, 1 minus 1. This by this, or maybe I should say transpose here. This by this is 1, this by this is minus 1, so that gives you 0. So the one diagonal is orthogonal to the second diagonal. E1 minus E2. Okay. Let's draw pictures. This one says, well, the angle here is 90 degrees. That's what it says. This calculation. This calculation says, if you were to look at these two axes, this is 90 degrees. Okay. Reasonable. Now, what you can do is, instead of first consolidating these terms and then doing the dot product, you can just expand. Okay. I'll do that too. Instead of first consolidating and then dotting, first expand. So you have a dot here, distribute. This is the same thing as E1 dot E1 minus E2, and then plus E2 dot E1 minus E2. Okay. Now you distribute the other way around. This gives you E1 dot E1, then minus E1 dot E2, then plus E2 dot E1 minus E2 dot E2. When you're dotting two vectors, it doesn't matter in which order you dot. This is the same thing as this. This is 1. This is minus 1. So you get 0. Okay. You can do it that way too. Lots of fun. This cancels out with this. Okay. Now note that E1 dot E1, I'll continue here, is just 1. So the norm of E1 is E1 dot E1 in square roots. Then you dot this against itself. 1 times 1 is 1. 0 times 0 is 0. So this is just 1. So that means that the norm of E1 is 1. Certainly the standard basis vector should have magnitude 1. Okay, that's what this says. Okay. Okay, let's do one more thing perhaps. So the norm of E2 is going to be 1 also. Maybe I should add that. If a vector has norm 1, you call it an unit vector. So and in fact, if you have a vector space and a basis such that any two vectors in that basis is orthogonal to each other, that's a orthogonal basis. And if in addition each of the vectors have norm 1, you call that a orthonormal basis. We'll get there later, but these are also sort of terms that we're going to need to use. Let's try to compute E1 against E1 plus E2. Okay. So I want to dot this. In fact, let's do it like this first. Let's first compute the norm of E1 plus E2 over here. E1 plus E2 norm is 1, 1 norm. What is this? You tell me. Mm-hmm. Question? Or? Oh, okay. Does this make sense? Well, yes, because E1 plus E2 should be this vector over here, right? This guy. This is E1 plus E2. And certainly here you have this right-angled triangle, and you have the Pythagorean theorem, whatever. Okay. So this inner product you can think of as abstracting out the main idea of the Pythagorean theorem. Any questions about this? Okay. Now let's look at the angle between E1 and E1 plus E2. That is to say, this angle. Certainly it should be 45 degrees. That is to say, pi over 4. Right? So what do I need to do? I would suggest don't worry about this arc cosine. Look at inner product divided by norms. That's easier to look into. So what is E1 dot E1 plus E2 divided by E1 norm E1 plus E2 norm? Now this, again, if I want, I can just dot this with 1, 0 to get it. And in fact, let's do it that way. This is 1, 0, this is 1, 1. The numerator is going to be just 1. The denominator is 1 times this guy. This is 1 over root 2. So the angle between E1 and E1 plus E2 is whatever the angle is, whose cosine is 1 over root 2. That's 45 degrees. So cosine of this angle should be this, which means this angle should be 45 degrees. Okay. So whatever this inner product business is, and angles and distances and all that stuff, it just matches with your intuition. Okay. Let's do one more example. What is the distance between E1 and E2? I'll do it here. So distance between E1 and E2, well, this is the norm of E1 minus E2. Which I hope you would agree with me, that is root 2. And again, this makes sense because I'm looking at this thing, right? So this is E1, this is 1. Here is, again, 1. This is E2. And this distance should be the length of this line segment. And certainly if this is 1, this is 1, this is right angled, this length should be root 2 again by the Pythagorean theorem. So all of these ideas somehow, work to generalize Pythagorean theorem type statements. Just like in standard geometry, this Pythagorean theorem and all that stuff is useful. In general too, it is rather useful. And the same angle formula is going to work in the context of regular geometry as well. So maybe we can come up with an example to exemplify that also. I'll just do it here. I guess it's better to start with the geometry. Nope. Say I want to take two unit vectors in the plane that are separated by, let's say, 30 degrees, something like this. This is the first one, this is E1, and then I want to have another one that has a 30-degree angle here, okay? So this is E1, this guy here is V, and I'm saying that this angle should be 30 degrees. Okay. So based on this, I want to compute perhaps, I don't know, the distance between V and E1. Okay. We can do that certainly. So what is happening? It's something like so. I'm just going to draw a bigger picture. Right. So you're given this. I'm asking, what is this length? In other words, I'm asking what the distance between V and E1 is. Now, if you're familiar with plane geometry, what you would do probably is you would draw this perpendicular line, do some sort of like a Pythagorean theorem, whatever, to come up with this other angle, other length. But what we can do is we can go ahead and try to compute it using the new rules that we have. So d E1V by definition is E1 minus V in norm. Okay, this is the same thing as, well, I'm going to take the squares first. It's easier. E1 minus V dot E1 minus V. This is E1 dot E1 minus this by this, this by this. Okay, so we have this by the rules. E1 dot E1 is the norm squared of E1, but since E1 is of unit length, this is just 1. This is also just 1, because I know that V is on the unit circle. So somehow I need to compute this dot product. So this is minus 2 times V dot E1. Okay. Now what is this V dot E1? Whatever that is, it should be the cosine of the angle between them. Okay? Because the denominator in this case is 1. And so because this is 30, I'll write it here, because I'm given that the angle between V and E1 is 30, I know that cosine of it is cosine of this guy. So this by this, I believe it should be 1/2. No, it should be √3/2. But this should be the same thing as this, which means this should be minus √3. But of course, in order for this to be positive, I need to take the absolute values here, so that this is plus √3. And I don't need to look at these anymore. Okay. Good. It should be something similar to this, if this is not exactly correct. I hope you get the idea. You can just use like these ideas in pretty much the same way you used in sort of plane geometry, do all this stuff. Maybe if you want to verify this, what you can say here is that you can call this length x. Yeah, okay, so because this is 30, 60, 90, I know that this length is 1/2, and this length is √3/2. This should be 1 minus this. And then you can apply the Pythagorean theorem to get something else. Which makes me think that maybe this number is not quite correct. But anyway, you can do a bunch of shenanigans like this. This inner product stuff is really nice. Once you have this inner product or dot product, you have the norm, you have the distance, you have the angle. In particular, you have what it means. You have a sense of what it means for two vectors to be orthogonal. Really what matters is this orthogonality for us. Okay. Comments or questions? Okay, I think it's a good place to stop for today. We're going to continue on Friday. Thank you. All right, let's start. Good morning. I take attendance today. So we had started talking about this orthogonal stuff, orthogonality. The main idea was this inner product, and downstream from it, we had a bunch of different notions. I'm going to do a review, and then I'm going to introduce some more sort of terminology. And at the end of today, I would like to mention the second version of the fundamental theorem of linear algebra. Remember, the fundamental theorem of linear algebra said rank plus nullity of any matrix is the same thing as the number of columns, which is the same thing as the dimension of the input space. We want to upgrade that using orthogonality. So I'm just going to stick to the Rn case. I should mention, I made some calculation errors in the last example that I was discussing on Wednesday. Whenever I sort of rush, I end up sort of hallucinating some wrong calculations and stuff. And some of your colleagues at the end of last class came up to me and said, oh, you know, you made an error here and stuff like that. So I want to take my time and, verify that indeed things work as expected. I have a piece of gum because I was proctoring an exam in my other class earlier, so. Okay. So, inner product, okay? This is a bunch of different notations. We just want to look at the Rn case. Inner products are always going to be scalar valued. So you're going to feed to it two vectors. It's going to give you a number, okay? So uv vectors in Rn, okay? Let's just forget about this relativity stuff so that we think of u and v as n by ones. Their inner product or dot product is written like this. U comma v embraces, this is one notation that you might see. I personally prefer this. In physics sort of terminology or physics literature, instead of a comma, they put a bar. And they call this the bra-ket notation. So this is the bra part and this is the ket part. They split this apart and stuff like that. Or the more multivariable calculus notation is u dot v. Okay? This kind of gets confusing in my opinion, but it's very common also. And what is this? Well, u is an n by 1 and v is an n by 1. Somehow I want to combine them together in a nice linear algebraic way, and I want to end up with a 1 by 1. In other words, I want to end up with a number. Well, what you can do is you can take the transpose of this u to get a 1 by n, then multiply. U transpose v. Okay? So let's write it. This is u1, u2 dot dot dot, un transpose v1, v2 dot dot dot, vn. Okay, how do you do this multiplication? This by this plus this by this and so on. Okay, u1, v1 plus u2, v2 plus dot 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 plus un, vn. So you see that's a scalar. It's a 1 by 1, but let's not put the parentheses to think of this as a 1 by 1 matrix. Let's just think of it as a number. Okay, this was the inner product. Once you have inner product, you have something called the norm. And all you need to do is to dot any vector with itself and then take the square root. So okay, u against itself, then take the square root. And again, if you open this up following the rule, this just gives you this. Right, so u1 squared plus u2 squared and so on. And then you take the square root of everything, which I hope you would agree with me is sort of like a generalization of the absolute value function, right? So if I had one entry only, taking the square of a number and then taking the square root gives me the absolute value. If I had two of these, that's just the Euclidean magnitude. All this says is that this works in general, in arbitrary dimension, okay? That was norm. The next thing is distance. So the distance between two vectors u and v is nothing but the norm of their difference. So you look at the vector that is u minus v, that's a vector in and of itself, take its norm. Okay? Opening this up again explicitly gives you that all you need to do to compute this distance is to look at the differences of their entries, take the squares of them, add them up, and then take the square root. So u1 minus v1 squared plus u2 minus v2 squared plus dot 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 plus un minus vn squared and everything in a square root. And that's the distance. What else? Angle is this. Instead of using the arc cosine, I'd rather keep it as a cosine. So I like writing it like this. So I'm going to look at u against v. Then I'm going to compare it to the product of the norms. There's going to be a factor that's going to give me the angle. Okay, that's how I think about it. So this is going to be the cosine of the angle between u and v. And if you want to solve for the angle, you can certainly do that. What is this? So inner product divided by the norms. Oh, and then I need to take the arc cosine. You can think of this in either way. I personally prefer this more. This is somewhat more nasty, I think, but to each their own, of course. Okay, angle. So we had this important inequality, CBS inequality. It's basically related to this. Cosine is some number that is between -1 and 1. So if I were to erase it from the right-hand side, I would have an upper bound. So that's CBS. So u against v, inner product in absolute value is upper bounded by u norm times v norm. This is like very important. We can also say, in fact, there's a Pythagorean theorem in this context. Or maybe even before that, I should mention orthogonality. Now that I have the notion of an angle, orthogonal vectors or perpendicular vectors should be vectors whose angles are 90 degrees. And so when you plug in 90 here, cosine of 90 is 0. Okay, so right-hand side is going to give me 0. And that gives me the notion of perpendicularity given any inner product. It says u and v are perpendicular if their inner product is 0. So I'll write it here. U perpendicular to v. And so you use this perp symbol. U perp v is the same thing as saying that u against v is 0. And you have the Pythagorean theorem. It says the standard thing that you expect. So if you have a u here and a v here, somehow you want to look at this length. You want to think of the triangle given by these two guys. And you want to say, this is a right-angled triangle if and only if something happens. Well, Pythagorean theorem essentially gives you the condition that is necessary and sufficient for this angle to be 90 degrees. And so how are you going to do this? Well, the length or magnitude of this vector is nothing but u norm, okay? And the magnitude of this vector is nothing but v norm. And the magnitude of this is u minus v norm, okay? Right, because if I were to go from 0 to v using v, and then how can I go from this point to this point? Well, to v, I need to add u minus v. So the length of this should be the difference. In other words, it's the distance between the two vectors. And so Pythagorean theorem would say that this angle is 90. In other words, u and v are orthogonal if and only if the square of this is the sum of the square of this and this. You can put plus there too, actually. It doesn't matter. Says u perp v is the same thing as u plus v, let's say, in norm square is the same thing as u norm square plus v norm square. Okay. I'm not going to prove this. You can just take it for granted. This was all the definitions that we defined so far, we used so far. Suffice it to say at this stage that whatever geometrical intuition you have regarding the plane, this stuff allows you to generalize everything to higher dimensions in linear algebra. Okay? Any comments or questions about this? Okay. Now, I want to go back to this example I was doing on Wednesday. What I did was this. I looked at E1 on the plane, so 1, 0. That's a unit vector. Its norm is 1. So maybe I should add it here. Okay, that's the definition of a unit vector. And then I took another unit vector, which I called v, and I said, say the angle between these two vectors is 30 degrees. And the point of the exercise or the example was to compute the distance between them. So first, I'm gonna actually do it in two ways. I'm gonna do it once using trig and basic geometry, and I'm gonna again do the same thing using inner product stuff. So say E1 is 1, 0, and V is given by the picture, right? So that's my unit circle on the plane. Here is E1. This guy is E1. And I have another vector here, V. It's again a unit vector. And I'm saying, let's say that this angle here is 30. Okay. The point of this exercise is or example is to compute the distance between them. So what is d of v comma E1? Okay. Now let me just zoom in onto this triangle here. So it's like this. Okay. So this is my 0. This is E1. This is V. Okay. Since both of these are on the unit circle, I know that for this triangle, this length is 1, and this length is also 1. And I also know that this angle here is 30. I'll write these. This is 30 degrees. This length is 1. And this whole length is also 1. And what is this? Geometrically speaking, it is nothing but the length of this line segment. So the length of this is what I'm trying to find. Now, let's just first try to compute this using plane geometry methods. You need to know this, of course, but one of the nice angles is 30 degrees in this business. Because if you have a 30 degrees as one of the angles, then you can sort of, if you can create a right angle triangle, then you have some nice relationships between the lengths of the sides. So what you do is, for method 1, you add this rectangle, this height, I guess, and then you look at this right-angled triangle. Because this is 30 degrees, you know that the length of this is half the length of this. And again, by the Pythagorean theorem, you know that the length of this is nothing but the square root of this, or the square of this minus square of this. So the length of this little piece is going to be root 3 over 2. But since I know that this whole length is 1, this remaining segment should have length 1 minus this. Which then would allow me to use, again, the Pythagorean theorem to compute the length of this using this side and this side. OK, let's do it. So I'm going to call, we'll use green here. This length I'm trying to find, L. So this is L. And I'm trying to find what it is. Okay. So what is L? Well, because Pythagorean works with squares, it's better to first compute the square of it, I think. L squared is the same thing as the square of this length, which is 1 over 4, and then the square of this length. So all I need to do with it is to add these up. 1 over 2 squared plus 1 minus root 3 over 2 squared. OK, expand everything. This is 1 over 4 plus 1 minus root 3 plus 3 over 4. These two give me another 1, so that's a 2. So I have 2 minus root 3. But I was computing L squared. To get L itself, I need to take the square root of this again. So L is 2 minus root 3 all in 1 square root. That's a length. Okay, and I know that this is a nice number because 2 is 4. The square of 2 is 4. So I can think of 2 as square root of 4. And so this is going to be a positive number. So this is a well-defined thing. Everything is nice. That's what I should have said last time. Okay. How many of you are familiar with this method? OK, most of you. Very good. So it's perfectly available. But the point of linear algebra, of course, is now you want to do the same thing in 50 billion dimensions. OK? And so therefore, you're going to need sort of some technology. And what I'm saying is that once you use this, once you get comfortable with inner products and all these other structures that are downstream it, you're going to be able to essentially use the same reasoning in arbitrary dimensions, even in infinite dimensions, actually. But we're not going to use that much. So that was the first method. I want to calculate the same thing using only inner product stuff. And so your enemy in this business is going to be this phenomenon of the princess being in another castle. You're going to say, oh, I need to compute the distance. What is the distance? Oh, it's the norm. What is the norm? It's this other thing. So you're going to keep chasing the definitions for a while at least. But at some point, it sort of clicks. That has been my experience. So this is the second method. OK. I want to compute the distance between V and E1. All I know is that the norm of E1 is 1, norm of V is 1, and the angle between them is 30. Okay, so what I need to do is I need to rewrite this distance in terms of these three given things to me. These three things that were given to me. So by definition, and in fact, I'm going to take the square of it. Now this is V minus E1 squared by definition of the distance. But I know what this is because the norm of something, right, is the vector inner producted with itself and then take the square root. If I'm taking the square here, all I need to compute here is, well, I need to compute V minus E1 against itself. Okay. You can expand. So this inner product is what is called bilinear. Okay. So it is linear in this entry. It is linear in this entry. You can expand everything. Okay. So I'll do this one step at a time. First, expand this. The minus E1 against V minus E1. Then I'm going to expand in the second entry both this and this. V against V minus V against E1 minus E1 against V plus E1 against E1. Okay. But any vector dotted against itself is norm squared. So this is V norm square. This is E1 norm square. And when you're dotting two things, it doesn't matter in which order you dot them. So you can sort of flip this and collect these terms. And so you have V norm squared minus 2 times V against E1, collected these. And then I'm going to have plus E1 norm squared. I was given that both V and E1 are unit vectors. Their norm is 1. So this is 1. This is also 1. In total, I have 2 minus 2 of the inner product. Okay. Now the final thing we need to use is, well, the angle information. Based on this, you see, I need to say something about this. Well, it says V against E1 is V norm times E1 norm times the angle between. What is the angle between? It is 30. What is cosine of 30? You can see it here. This by this is root 3 over 2. This is 1. This is 1. So the inner product is 3 over 2, root 3 over 2. So that I take and put it here, which gives me 2 minus root 3. I was computing the square of the distance, which means if I were to take the square root of this expression, I get again the distance. Okay. So somehow, mysteriously, this inner product sort of abstracts out all the properties that you're using, that you're possibly comfortable with, from plane geometry and trig. So pretty good, okay? Which consequently means once you have an inner product available to you, or dot product, whatever, now you have geometry available to you, okay? Any questions or comments about this example? It seems like this inner product stuff is not, at least like, you know, computationally speaking, not very sophisticated, but somehow the complications sort of creep up on you, in my experience. So you want to be careful with that. Because ultimately we're going to sort of put these back in with eigenstuff. So. Okay. Comments or questions? Yeah.
Why did you decide to square the distance at the start?
Yeah, because if I didn't, then I would have been taking the square roots all over the place. I don't like carrying around square roots. I say I'm just going to first compute the squares. Then at the final step, I'm going to take the square root.
Okay.
Because otherwise, if I didn't put square here, there will be a square root here, square root here, square root here, and so on. Yeah. I should also mention, some of you might have heard this phrase, least squares approximation. This is like a fairly common thing to do when you're trying to approximate something. This least squares is sort of like one of these cost functions that you end up trying to minimize. The reason why they call it the squares is this too also. Somehow with this inner product, when you look at the distance between two things, whatever, there's always this square root. Or you look at the square of things. Part of the reason is because instead of looking at the distance, often it's better to look at distance squared, because distance squared is a differentiable function, which means you can do calculus much easier. So down the road, there's those things as well. But yeah. Any other comments or questions? Okay, now we have inner product, norm, distance, angle, CBS. We talked about orthogonality, what it means for two things to be orthogonal, Pythagorean theorem. Now I want to talk about perp operation, okay? And this is where things are getting really interesting, in my opinion. If I have a set of vectors in a vector space with inner product, I'm going to define something called S-perp. Say the set is S. I'm going to define a set called S-perp. Be a vector space with inner product. Okay? You have an inner product defined as well. So the dot product is defined. For S, a set of vectors in V, you write it like this. S raised to the power perp, and you read it S-perp, is the set of all vectors in V that are orthogonal to each vector in S. That's a mouthful. Let's try to think of examples. Well, I should say this. For this business, I think the first thing to remember is things like, you have a shape, and then you start thinking about the normal vector to that shape. Say you have a line. So for instance, if I have on the plane, say we consider this, this one. Okay, this is of course y equals x, but I rather would write it like this. X minus y equals 0. Okay, this is the same thing as writing, 1 minus 1 xy is 0. Right? When I dot these two, x minus y, add them up, you get x minus y. That means a point xy is in this line if and only if it is perpendicular to 1 minus 1. Okay? And so if I were to choose my S to be this specific vector, it's a set of one vector only, its perp would be precisely this line. And of course, what is this? 1 minus 1, it is nothing but a normal vector to it. Right? It's a vector that is orthogonal, that is perpendicular to this line. Yeah, I'll write it like this. So I can write it like so. 1 minus 1 as a set, perp is the same thing as y equals x. Make sense? This ends up being very useful in calculus, for instance. In calculus, you end up needing to use normal vectors, not only to lines and planes and whatever, but also more complicated shapes. But of course, I can do this in higher dimensions as well. I can look at the equation of a general, say, plane in 3 dimensions. Here's another example. So if my vector is, say, ABC, it's a vector in R3, then this perpendicular, so the V perp, is nothing but xyz's such that, well, ax plus by plus cz equals 0. So this is an equation of a general plane passing through the origin in 2 dimensions. Okay? And the picture always is, well, this is going to be your normal vector, imagine. V is pointing this way, and you look at the plane perpendicular to it. As you vary V, the plane moves accordingly. Right? Make sense? Let's look at special cases of this. In 3 dimensions, we have 3 distinguished planes: xy plane, xz plane, yz plane. Right? I'll continue here. So E1 is 1, 0, 0. E1 perp, all those vectors that are perpendicular to 1, 0, 0, right? So when you write that down, it just says x equals 0. X equals 0 is the same thing as the yz plane. Okay. So what is happening here? This is x, this is y, this is z. Well, you're choosing the yz plane, okay? And this is E1. This is E1, this is its perp. Okay? If I were to look at E2 perp, right? E2 is the vector in this direction. It's going to give me the xz plane. If I were to look at E3 perp, it's this vector. Its perpendicular is going to give me the xy plane. Okay? But of course, I could have done something else. I could have looked at 1, 1, 0. I'll perhaps draw that, or try to draw it. Well, let me draw it this way. In this business, in my experience, if you first draw the coordinate system, it becomes harder to draw things. So I would suggest not drawing the coordinate system. We know at this point we can do this. Right? There's a way to think about all this stuff without actually choosing your basis. But for instance, 1, 1, 0, well, I'll do it this way. I have this plane in 3 dimensions. This is x plus y equals 0 in 3 dimensions. Its normal vector is 1, 1, 0. (90 degrees). Okay. So more generally, I'll draw the picture that corresponds to this. We have a plane. A typical plane passing through origin has equation ax plus by plus cz equals 0. Its normal vector is going to be, or one of its normal vectors is going to be abc. Okay. If you want to, so these kind of things end up being useful in calculus too, of course. Typically, this perhaps would also gives you, say, the velocity vector. And then if you have sort of like a particle moving in 3 dimensions, you want to talk about how it rotates as it's moving as well. So you have things like torsion and stuff. And so those have to do with this perpendicular plane. So this ends up being rather useful all over the place. The point, of course, is that you don't need to just stick to 3 dimensions. You can do it in arbitrary dimensions. But this is sort of like a first example, I think. Yes?
How would it change if x, y, and z didn't equal 0?
Well, then it would be a plane that is not necessarily passing through the origin. Yes, but that's a good point. No matter what the set is, whenever you take the perp of it, you always get a linear subspace. S-perp is always a subspace. Yeah. So maybe I'll add it here. A couple of statements. So no matter what the set S is, the moment you switch over to S-perp, it's going to be closed under linear combinations. So S-perp is always a subspace. I actually came up with a couple different exercises similar to this. Kind of fun. You might call this also the orthogonal complements if S is a subspace to begin with, but you don't have to in principle. One thing you can do is you can double perp. As perp is the same thing as a span. Okay. And S-perp is the same thing as a span of S-perp. Some funny business. Okay. I think I want to try to make sense of this expression. In this case, for instance, our S consisted of one vector only. Once we take the perp of it, we get this line, y equals x. That's a span of 1, 1. But then, when you take the perp of this, what are all the vectors that are orthogonal to this? Well, you're going to get back this whole line. So you see, if I start with 1, 1 as a single vector, take double perp, now I have the span of 1, 1. So 1, 1, perp is the same thing as span of 1, 1. Pretty cool. Why does that work? Because ultimately, perpendicularity is about inner products, and inner products are linear in both of the entries. So that's ultimately the reason why these shenanigans work the way they do. So that's pretty nice. Comments, questions? Oh, I want to add one final thing. If I start with a subspace of V itself, if, say, W is a subspace of V, then the dimension of V and the dimension of V perp is going to add up to the dimension of, oh sorry, dimension of W and the dimension of W perp is going to add up to the dimension of V. Pretty cool formula. We're almost there to state the second version of the fundamental theorem of linear algebra, but I'd rather give a couple more examples that are slightly more complicated. Let's see what happens if we take more complicated subspaces, perhaps, and look at their perp. So in 2 and 3 dimensions, you see all of these things work as you expect them to. They match with your intuition. In higher dimensions, now it's not as easy to visualize, but linear algebra is always helpful. So you want to be able to sort of do the same things using linear algebraic formalism. So let's say we're in R4, okay? And I'm going to take, say, as W, the span of E1 and E3. Okay, so I have 4 standard basis vectors. E1 is 1, 0, 0, 0. E3 is 0, 0, 1, 0. Okay, these are linearly independent. When I take their span, that's a 2-dimensional subspace of R4. Okay, here's a 2D subspace in R4. I want to compute its perp. Okay, well, what is the perp of W? It's a set of all those vectors that are perpendicular to any one of these vectors. Well, what needs to happen is this. I should be able to take an xyzt 4-dimensional vector, dot it against any vector here. As a hint, as a sort of nice way to do this, once you have a basis for your space, all you need to do is to dot against the basis vectors. That's going to be sufficient. Okay. I want this to be 0. But when I do this dot, this is just x. So x has to be 0. And xyzt dot 0, 0, 1, 0. Again, this is just going to give me z, the third coordinate. I need this to be 0 also. So xyzt, a 4-dimensional vector, is in W perp if and only if the first and third vectors are 0. In other words, if it's in the span of E2 and E4. Okay? So we can just write it like this. Okay, so what is happening here? We have this W. It's the span of 2 of these standard vectors. It's a plane, but somehow perpendicular to it is W perp. Okay, so this is the E2 axis. This is the E4 axis. Of course, I'm drawing it like this, but you should imagine that this is one plane, this is another plane, and the only point they intersect at is the origin. Okay, so it's kind of harder to visualize what is happening when the dimension is higher. So maybe I should say This is a plane. Okay, this is a plane. And they intersect only at the origin. Okay. So comments, questions? Well, I hope you would agree with me if I were to tell you, well, if W, if the subspace is more complicated or the set is more complicated in terms of algebra, then to compute W perp, well, you're going to set up certain equations, and again, you're going to do row reduction, whatever, to solve them. You see, it again goes back to row reduction, but now we have sort of a higher order interpretation of what is happening. Do I want to start? I have a couple minutes. I think what I want to do is I want to start thinking about a certain example. Because ultimately, now I want to bring into the mix, or bring this into the mix, and state another version, an upgraded version of the fundamental theorem of linear algebra. Okay? And to do this, we need to first realize that fundamental theorem of linear algebra works both for a transformation and simultaneously for its transpose. So somehow, this perp upside down t is related to t, which is a transpose. Okay? Ultimately, what I want to do is I want to take the perp, say, of the column space of a transformation and perp of the null space of a transformation. Somehow, the perp of the null space of a transformation should be related to something related to the A transpose. So I think a good example is something like this. Say A is 1, 1, 0, 0. Maybe like this. Okay. The column space of it is the span of its columns. So it's the span of 1, 0. This is the column space. Null space of A is when x plus y equals 0, which means it's here. That's the null space. Okay. Now, if I were to look at A transpose, probably I'm not going to have time to finish this. A transpose is a transformation that goes the other way around. And the second fundamental theorem, or rather the fundamental theorem that we're going to state later, probably on Monday, is going to say, well, the null space of A transpose is going to be the perp of column space, and the column space of A transpose is going to be the perp of null space. Okay. Very mysterious, but very useful. Okay, that's it for today. I'll see you on Monday. Thank you.